Hello friends, myself Dr. Girish Kun, Assistant Professor from Mahatma Phule Arts Science Commerce College, Panvel. Today we will discuss the nomenclature of crystal directions and crystal planes. First we will see the specifying point in a crystal. Over here at the right side, one unit cell has been shown with the three crystallographic axes x in this direction, y in this direction and z in the upward direction. And with the unit cell having the corner points. Now in order to specify the point in a crystal, first of all we have to find out the distances of that point along the x-axis, y-axis, z-axis. So this is the first step, and the distances must be measured in terms of translation vector a bar, b bar and c bar. So once we get the distances in terms of a translation vector, the point is represented by 1/2 1 1/2, as its distance is a 1/2 a bar, 1 b bar and 1/2 c bar. So corresponding indices we have to consider to represent the point in a crystal, and that distances must be enclosed, or this number must be enclosed in a circular bracket. Similarly, for simple cubic cell, the atoms located at the corner. So the positions of the different corners has been specified over here. Like in a circular bracket, the atom is at origin must be represented by in circle bracket 0 0 0, and similarly other atoms we can represent. Or for the body centered cubic cell, the center atom over here, the center atom is located at 1/2 1/2 1/2 in circular bracket. Why? Because the body centered atom can have the distances along the x-axis, y-axis and z-axis is nothing but the 1/2 a bar, 1/2 b bar and 1/2 c bar. So that's why the corresponding indices, corresponding numbers will be 1/2 1/2 1/2, and that's supposed to be enclosed in a circular bracket. So in this way we can represent the certain point in a crystal. Now we will discuss the specifying direction in a crystal. To specify certain direction in a crystal, generally three indices enclosed in a closed bracket, which is a square bracket, and that indices must be u, v, w. So in this way we can represent the any direction in a crystal. So specifying direction is something different than the specifying point in terms of the square bracket has been used over here. So this is the difference between specifying point and specifying direction in a crystal. So again, to find out the direction in a crystal, we have to do the some steps. First of all, we have to find out the translation vector along the chosen direction, such that the tail is must be at origin. Find out the distance PQR traveled in terms of unit translation vectors A, B, C. So PQR will be the distances traveled in terms of unit vectors A, B, C. After that, then we have to choose the least integer from the PQR. We have to choose the least integer from the PQR. Like if the distances is 2A, 4B and 6C, so in that case least integers will be 1, 2, 3, so that the ratio u as to v as to w will be kept same as the p as to q as to r. So these indices u, v, w express the directions of the vector in a crystal. So then the direction will be written in a square bracket with the indices u, v, w, which is we have opted in this in the specified process. So over here you can see in the two-dimensional lattice, the OP can be represented by over here one can find out the first of all distances. So O is the origin, so along this axis we can take a x axis, and along the upward direction we can take a y axis. So in that case the distances will be the 2a and 2b. So least integers will be 1a and 1b. So u v values, or u and v will be 1 1, and w will be 0, as the z axis is absent. Okay, so similarly for o dash p dash, so similarly for o dash p dash one can find out the distances p q r. So p will be 2a, and b will be sorry, q will be 1b, and r will be 0 c. So that the least integers will be 2 and 1 in this case. So the direction we can represent o dash p dash direction we can represent by 210 in a closed square bracket. Now I will leave the assignment to you people to find out the direction o double dash p double dash. Over here you people can see the unit cells are there, and the back bottom corner atom is or point is considered as origin, and from that origin three crystallographic axis has been shown, and the unit cell is placed on these crystallographic axes. Now over here, sorry, now over here we have to find out the directions OR and OS. So as per the process, first of all we have to put the tail at the origin, which is already did over here. So now the rest of things that we have to find out the distances, and then we have to convert it into the least integers. Okay, so or is the vector, so it have the distance only along the x direction, and for y direction and z direction distances it will be 0. Okay, so that x will be 1, y will be 0, and z will be 0. These are the pq distances, and so that the least integers will be same 1 0 0, so that the direction or can be represented by in a square bracket 1 0 0. In the another case, one can see the origin is represented the front bottom corner, so that which is the ON. So in this case, what we have to do, we have to find out the distances first of all along the x-axis and y-axis and z-axis. So as we know, the vector is in a backward direction, so that x-axis distance will be minus 1a, y-axis distance will be minus 1b, which is from over here to in this direction. So minus 1b will be there, and x-axis distance will be minus 1a, and z will be 0c. So that minus 1 x is there, minus 1 distance along the y direction is there, and along the z direction it is a 0. So now the we have to represent this indices by the specifying bar on its head. So 1 bar and 0 in a closure bracket can represent the direction of ON vector or ON direction. Okay, so this is the how one can find out the direction in the crystal. Now coming to nomenclature of a plane in a crystal, we have seen how to find out the point, then we have discussed how to find out the direction. Now we will discuss the nomenclature of a plane in a crystal, which is generally represented by Miller indices. Miller was a scientist, and he developed a method to designate a set of parallel planes, to demonstrate a set of parallel planes in a crystal by three numbers in a uh, circular bracket, enclosed in a circular bracket, which is the HKL, and these numbers, three numbers, is known as the Miller indices, and these Miller indices used to represent set of parallel planes in a crystal. So if we consider this is a crystal, so one can see the horizontal planes are there, so one can consider this is a one set of parallel planes, or another the horizontal planes set is that. In the case of this case, one can see the triangular planes has been represented. So all these planes can be represented by a single number of set, and that single number of uh, uh, single number of set is known as Miller indices, which is to represent the set of parallel planes. So now we will see the steps to determine the Miller indices of a set of parallel planes, which is as follow. First of all, we have to consider the crystallographic axes x, y, z, which has been represented with their unit translation vector a to a, 3a, and then b, and then c along the z axis. So unit translation vectors has been represented. After that, the one plane has been demonstrated, which is going to cut along the x-axis at a 2a, then along the y-axis at the 3b, and along the z-axis at the 1c. Okay, so this is the information that we have. Now we have to find out the Miller indices for this plane, which is a representative plane for all the planes which are parallel to this plane. So let us determine the Miller indices for this given plane. So first of all, in order to find out the Miller indices, we have to determine the coordinates of the intercept made by the planes along the three crystallographic axes. So we have to find out the coordinates, okay, along the different crystallographic axes. So along the x, y, z, the coordinates has been represented over here 2a, 3b, 1c, which we already discussed. So distances p, q, r one can find out, which is a 2, 3, 1. So now we can express the intercept as a multiple of the unit cell dimension, as a multiple of ABC, or the lattice parameter along the axes. So after dividing the distances in terms of translation vectors by the unit cell dimension, that is ABC, we will get the coordinates. We will get the numbers 2, 3, 1. Now in the next next steps, we have to take the reciprocal of the obtained numbers. So the reciprocal of the 231 will be 1 upon 2, 1 upon 3, and 1 upon 1. Then we have to reduce this reciprocal to the integral number. We have to reduce this reciprocal numbers to the integral numbers. So how one can do that? By multiplying the least common multiplier to this number. So LCM is the one number. After multiplying to this reciprocal, we will get the integer. So the LCM of the 231 is a 6. So when we multiply the 6 to this reciprocals, we will get the three values, which is nothing but the integral numbers 3 to 6. So these are the values of h, k, l respectively. So one can enclose these three numbers, three indices into the circular bracket. So the 3 to 6 enclosed in a circular bracket is nothing but the Miller indices of the given plane as shown over here. So this is the how one can find out the Miller indices. So now over here one can see the different planes has been shown, and corresponding Miller indices has been written on the different planes. Okay, so these Miller indices are the representative number set of numbers for all planes which are parallel to this plane. Okay, so how to so one can discuss how the Miller indices are obtained for the one particular plane, and then we will discuss about the others. So over here you can see this plane specifically intercept the y-axis only, and it is a parallel to z and x-axis. So as it is intercept will be for the y will be 1, then for the x and z, as it is parallel, So if we took the reciprocal of the three distances or intercept, we will get for x it will be 0 as 1 upon infinity, as this plane is parallel to x-axis, so it will never meet to the x-axis, so intercept will be infinity. Similarly for z-axis it will be infinity, so that 1 upon infinity will be 0, and for z also 1 upon infinity will be 0, and for y 1 upon 1 will be 1, so that the obtained and the LCM for the 0 1 0 is 1. So when we multiply that LCM to the these numbers, we will get the same number, and we have to enclose those numbers into the circular bracket. So 0 1 0 enclosed in a circular bracket will be the mirror indices for this given plane. Similarly, as this plane cuts the x and y axis, so intercept we will get a 1 1, and as it is a parallel to z axis, so intercept will be 0. So sorry, intercept will be infinity, so that its reciprocal will be 0. So that obtained in mirror indices will be 1 1 0. Similarly, over here, this plane measures the cryptographic axes at unit distances. So that's why it can be represented. Its mirror indices can be represented by 1 1 in a enclosed in a circular bracket. So thus, for this, I mean the gray planes also one can find out the Miller indices, as this is a cut to the z-axis. So x and y Miller indices will be 0, whereas for z it will be 0. Sorry, z for z it will be 1. So the Miller indices for this plane will be 0 0 1. For this, it is going to cut to the y-axis and parallel to the x-axis, similar to this one. So 0 1 0 will be the mirror indices of this plane. Coming to over here, this plane, one can see this plane is going to cut to the x-axis, uh, sorry, y-axis and z-axis. So we have to consider the plane which is parallel to the this one. So one can consider the front plane rather than the back plane. So now one can find out the intercept. Now you people can see the front plane is parallel to z-axis and y-axis, so their mirror indices will be 0 0, and for x-axis it will be 1. So the mirror indices of this back plane as well as the front plane will be 1 0 0 enclosed in a circular bracket. Thus the mirror indices may be defined as the reciprocal of the intercept made by the plane on the three crystallographic axes when we reduce them to the smallest number, smallest integer numbers. Okay. So over here the different planes have been given, and you people can find out the mirror indices for the given planes, and that will be the home assignment or homework to you people. Now what can be the intercept of HKL plane? So given ABC plane is a HKL plane, which is going to cut to the three crystallographic axes, or having the certain intercept on the three crystallographic axes. So we have to find out the distances OA, OB and OC along the three crystallographic axes, which is nothing but the intercept made by this HKL plane on the three crystallographic axes. So OA will be A upon H, OB will be B upon K, and OC will be C upon L. So you people can see OA is the ratio of is a unit translation vector and Miller indices. Similarly, OB is a ratio of its unit translation vector B and the ratio of Miller indices K. Similarly, OC. So the questions come in your mind, how this relation can be true, or how this relation can become. So in order to prove this one, we will see the one example, and then it will be realized. So let us consider this given a plane ABC, and it having the intercept 3A 4B and 2C along the three crystallographic axes x y z respectively. So reciprocal of this intercept will be 1 upon 3, 1 upon 4, 1 upon 2. So LCM of this intercept will be 12. So we have to after multiplying this intercept by the LCM, we will get the Miller indices 436. So the Miller indices of a ABC plane is a 436. So as per our earlier definition or our earlier formulas, OA, OB, OC in terms of unit translation vector and Miller indices, one can write over here in the same way. So OA is A upon H, so h is nothing but the 4. So a upon h will be 0.25a. Similarly OB 0.33b and OC will be 0.1666667c. So these numbers we will get, but the intercepts are not these having not these values. What the things that we are missing over here is nothing but the LCM, because this see, because you people know LCM is a common for all these ratios, right? So if, even though we have not considered this LCM, still this ratio becomes equal. If we multiply these ratios by the LCMs, still they will be having the same value. So that in order to get the same value 3a, 4b and 2c as an intercept, we have to multiply these ratios by the LCM. So OA, when we multiply the LCM 12, we will get the 3a. Similarly for OB and similarly for OC, we will get the same intercept as having in the plane. So that the intercept OA, OB, OC will be ratio of unit translation vector to the mirror indices. But we have to understand that in all these ratios, the LCM is a common factor that we have not considered. So that this will be the final relations between the intercept, Miller indices and the unit translation vector. And this relation is very useful in the our next points also. And thank you very much for listening this lecture.